Hey everybody, welcome back to another round of engineering, and yeah, let's get going. So we've completed everything from chapter 3, the analysis techniques of node voltage, mesh current, KVL, KCL, combining resistors, combining sources, the whole gambit. And so we're breaking into chapter 4 material. Now this is a circuit element that you have not seen before in previous physics classes. It is an active circuit element, so active. In other words, it requires an external power source in order to operate properly. So this is in contrast to your passive elements like resistors, like capacitors, like inductors. These are circuit elements that operate, if you will, due to the physical nature of how they're constructed. So they don't need any external power supplies in order to operate properly. So active elements, these things would be, well, probably this is the most common active element, I guess, and it's called an operational amplifier. Most people just abbreviate it as op amp, but it's operational amplifier. Okay. Now, the first thing that we should probably discuss is how do we indicate an operational amplifier on a circuit? We have the resistor, capacitor, and inductor, and of course you have your potential supplies, your current supplies. Okay. How do we do an operational amplifier? It's a triangle, so we'll start off. Usually I generally see it as a triangle pointing to the right, although I imagine that that's not standard. What is standard is that it'll have either 3 or 5 terminals. Okay. So here with our element that we've dealt with so far, these have all been 2-terminal elements. In other words, there's one connection on either side, and that's it. Your operational amplifier is different. It will have 3 terminals, 2 on the long side of the triangle and 1 on the apex, if you will. So if it has 3 terminals, this is what you'll see. 5 terminals, it's the same idea. You'll have 2 coming in on the long side. You'll have 1 coming out at the apex. And then you'll have 2 more, say, running perpendicular to the other 3 that have been drawn. Now, generally, this right-hand drawing is probably the more accurate one. And the difference between the two is that this right-hand drawing is also showing you the power inputs to the operational amplifier. So usually if you see these vertical lines, what this is something like your power supply, your positive and negative supplies that are powering the op amp. So they're missing on this left-handed figure simply for additional clarity. Okay. So if you ever see a 3-terminal op amp, bear in mind that there's 2 more places that plug in. It's just that they haven't been shown. Now you might ask, what do the other 3 terminals represent? Now usually the one at the apex, I believe I refer to it as V out. So the output potential. And then on the left-hand side, where these 2 come in, you'll have 2 symbols. You'll usually have a negative and a positive sign. Now, you might say, I know what negative and positive mean. We see it all the time in potential supplies. Don't kill a messenger. That's not what they mean here. Sorry. So negative refers to an inverted input, and the positive is the non-inverted input. I also like to, we'll see why those names come in as we work some more examples and start delving into the function of the operational amplifier. I do tend to think about the inverting input as being the, for lack of a better term, I'll put the negative feedback. And I guess this one, if, you know, since I'm just negating it, this would be the positive feedback. So this has nothing to do with the type of input they can accept, but rather it deals with what does it do with the input. So there's our V out, our output, and the two inputs. Let's go ahead. I will go and think about just the 3-terminal one for the moment. Okay. And we have the inverting, we have the non-inverting, and then we have V out. Okay. You might say, well, what is the purpose of an operational amplifier? How does it actually, what does it actually do in a circuit? And here's the cool thing. So the non-inverting input, I'll call it VA, okay, but you could think of it as the reference input. And you have VB, I'll put a second input, VB, into the inverting side of the amplifier. So this is going into the inverting side. In general, what this operational amplifier will do is output the difference between the two inputs. In other words, V out is going to be the difference between the non-inverting input and the inverted input. Notice again, okay, what have I done? Whatever VB is, I have a negative sign in front of it, so I've inverted. Okay. Now, generally, in addition to finding the difference between those two, there is generally some sort of scaling factor. We don't call it a scaling factor. Generally, what you'll see this expressed as is the gain. And that's where that amplification idea comes in, right? You feed a single signal in, the amplifier increases the strength of that signal. So that's where the amp part of the name comes from. Pretty cool, huh? So the question then becomes, how do I use this thing? What can I do with it? And we will find over the course of the next couple, say 2 videos or so, that we can use operational amplifiers to start doing mathematics. We can force operational amplifiers to do things like adding signals or subtracting, for example, signals. And also scaling, right? That's where that gain piece comes in. So all these kind of ideas are based on an operational amplifier. After our discussion about capacitors and inductors, we can return to the operational amplifier and find out that we can do things like differentiation. Differentiation. We can take derivatives, or we can do integration. So this, as the syllabus would suggest, is our starting point for getting circuits to do mathematics for us. Now, of course, there's other ways to do it and probably faster ways at this point, but this is the basics of it. You could build a machine to do addition or subtraction using op amps. Okay, well, we've got the basic functionality of the op amp. We have got what the terminals are labeled. Maybe we should talk about one of the very nice situations that arises when you're dealing with op amps. Okay. So again, we will have our inverting input, our non-inverting input. So inverting and non-inverting. We have our V out. And one of the cool things that starts to arise is when we start feeding, say I take a wire, I introduce a node, and I will go ahead and feed my output back to my input. Wait, what? Yeah. Let's think about this for a second. Now, we're going to have to put some resistors in and that kind of thing. But let's say for a moment we have VB and VA, so our inverting and our non-inverting input. Okay. Now, the function of the operational amplifier is that it takes V out as the difference between the two inputs. Okay. Now, let's think for a second. What does this node, so if I take that in a different color, okay, so there we go, node A here. Okay. If I take this wire and I run it back to the inverting input, the question is, what is the new potential of that inverting input? Okay. Yeah, you could see, well, we have the input VB, and then if we have this kind of feedback loop, we would get something like, well, the potential, and then I have the feedback loop, and oh, look at this. And so I end up with VA. And that's kind of the cool thing about the operational amplifier. We'll see how that's cool, is if you have a feedback loop, this wire, going to the inverting input, then the operational amplifier will set the potential of the inverting input equal to the potential of the non-inverting input. And that's what one of the golden rules is for analyzing operational amplifiers. So golden rule number 1. Okay. The inverting potential is equal to the non-inverting potential. Okay. When you have a feedback loop, this happens. So I'll put with feedback loop. Number 1. Okay. Now, number 2, golden rule number 2. Number 2. And this one I won't give any kind of proof for. Okay. But this will help us when we want to analyze things. Okay. No current into the inverting or the non-inverting terminals. Okay. So any current that meets an operational amplifier, say you're a nice little electron walking along from source B and you get to junction A, okay, the golden rule number 2 says that that current must take the feedback loop. In other words, it will not go into the negative terminal. Okay. That is not allowed. Okay. Now, I call this, just to be, so that you're aware, these golden rules are approximations. They are shortcuts that help make the analysis of an operational amplifier easier. Okay. Now, why do I say that? You know that in order for the op amp to know that the output is being cycled back to the input, right? The feedback loop is here. In order for the operational amplifier to know about that feedback loop, a little bit of information has to get back to it. In other words, a tiny little bit of current actually needs to go back into the input terminal to let the operational amplifier know that this feedback loop actually exists. I should not circle that. Okay. If that feedback loop, if the operational amplifier didn't get any current back into the inputs, there would be no way for it to know that that feedback loop exists at all. So it does take a little bit of current. But, and we'll see this in LT Spice, for example, these currents are on the order of something like picoamps or maybe nanoamps. Okay? 10 to the negative 12th or 10 to the negative 9th, something like that. Okay? And so what this means is, why is that important? The currents that we're dealing with will be on the order of maybe microamps or even milliamps. So compared to the amount of current that goes back into the inputs, we can basically just ignore it. We say, oh, those are too small. We don't need to know those. Okay. Be aware, though, if you're dealing with high sensitivity machinery, high sensitivity op amps, say for some reason you get into an electronics industry where you need a high precision, okay, feedback. Okay, be careful. There is a little bit of current. This golden rule will no longer apply, or you'll have to be more careful. Or if the currents get really, really small, so if they're not microamps, but they're rather picoamps, then all of a sudden you can't play with this golden rule. For the purposes of this class, you're okay taking these two and going with it. Notice also, I say nothing about the output. Okay. The output, you are perfectly allowed to have current flowing from the output channel. So you can have current coming in from right here. Okay, that is permissible. You might say, hey, wait a minute, Greg. If I treat golden rule 2 that no current can go into the op amp, but current can come out, doesn't that violate charge conservation? Right? Doesn't this violate KCL? And I say, yes, but remember, I have not drawn all the terminals here. There are 2 more terminals powering the operational amplifier, and those terminals will supply this extra current. Okay. So that's a second thing to be aware of, is you can have an appreciable amount of current coming from the operational amplifier, but no current going into the inputs. The excess, where does that extra current come from, is coming from the power supply of the op amp. Okay? Say, go ahead, think about that for a second. Make sure, convince yourself that that's okay. Let's go ahead and get some ideas about how to analyze these op amps using our golden rules. So let's, for a moment, let's go ahead, and this is probably one of the most straightforward op amps I can give you. Okay. So I'll do a couple of things. So I have my V out channel. I'm going to do a feedback loop. To my inverting. Okay, so there we go. And I'll call this R2. Let's do a second resistor, and then I will take it to a potential supply. And that potential supply will also go to ground. Call that R1, we'll call this V, and we have V out. Okay. So here's my mission for you. Assume that you have the values of V, R1, and R2. Okay, so assume that you have that. Using node voltage, I think node voltage is the way to go here. Node voltage, and that tends to be the technique that I use the most often for analyzing these circuits, just to let you know. Using node voltage, here's the question I have for you. What is V out in terms of the input potential, R1 and R2? Go ahead, take a minute, see if you can hack it out. You got it? Good, good, good. I know you've read about it. You'll see it again in lab. I want you to be familiar with this. You really need to know what you're doing here. So let's go ahead. We will go through, and I am going to label this one as node A. I'll label this one as node B as in boy. Okay. And let's see here. There we go. There we go. Let's get at it. Let's say for a moment that I would like to evaluate node A. So let's go ahead. We say VA minus V over R1, right? Notice I have that potential supply here. And then what else do I have? I have plus VA minus VB over R2 equals 0. Okay. Now, what allows me to do this? Remember, I assume that no current flows into the input. So I'm using golden rule number 2, right? I've taken care of the current flowing this way. I've taken care of the current flowing this way. I do not need to worry about the current going into the inverting input because of golden rule number 2. So I guess I should probably equal 0 because golden rule number 2. Hey, I guess you could say Greg Robison number 2. Okay. Golden rule number 2. Okay, good. Let's go ahead and think about what B would be. B as in boy. Well, what do we have? We have VB minus VA over R2. Right? And then, again, recall that we can have a current going into or out of the output current, or the output channel. So I'm just going to put plus I. I'm going to assume that there is a current that is going this way, which I'm going to call I. Okay. Equals 0. And last but not least, la pièce de la résistance, okay, is golden rule number 2, or 1. Golden rule number 1. VA must be equal to 0. Good. Right? Golden rule number 1 says that if we have a feedback loop, the operational amplifier will work to make sure that the potential of the non-inverting and inverting inputs are the same. My non-inverting input is grounded, potential 0. That must mean that my inverting input, the potential at the inverting input, must also be equal to 0. Nice, right? Well, in fact, notice also we have a set of linear equations, so we could do our matrix methods. But the fact that we know that VA is equal to 0, that will certainly make it easier to find VB right up here. Let's go ahead and do that. What do we have? We have 0 minus V over R1 plus 0 minus VB over R2 equals 0. And what do we get at the end of the day? We get that VB, the potential at B, must be equal to negative V, and now here's where I'll use a fraction here, negative V R2 over R1. That's cool, right? Look at this. We have now set up a small little circuit, and based on our values of the resistors, we can now control the output potential. That might sound a little familiar, right? Choosing a couple of resistor values, we can control the output potential. You've played around with a circuit element in lab where you control the resistors and you get a control over, I'll say, the output potential, or if you prefer, the output current. This is some of the function of your LM317 device. If I'm not mistaken, there are some op amps inside of that device. Okay. So then that's kind of the idea of what's going on underneath the hood. Well, how about the current? This is finding VB. How about the current, I? Well, let's get an idea there. The second one would be very helpful here. We get VB over R2 plus I equals 0. And so we find that the current flowing into the output channel of the op amp is simply equal to, well, we put VB to the other side, but then VB is negative. So we get V over R1. It should make some sense. If I look at just this part of the circuit, boom, right there, right? The potential supply goes from ground through resistor R1 to A, which is at ground, right? It should be, I mean, you could almost think of it as like, I have this. Well, in that situation, the current would be simply equal to V over R1. Cool, huh? Now here's one other, okay, so get your mind wrapped around that. Make sure you can follow that argument. And please bear in mind, we've applied both of our golden rules here to make our lives easier with the analysis. Okay, so I have two comments that now that we've gone through that example circuit, and incidentally, that's called the inverting amplifier. Okay. So inverting because the output is negative of the input, and amplifier because the strength of the signal, the magnitude, has increased or decreased depending on your choices of R1 and R2. Okay. Now there's 2 points I would like to make. Number one, so let's go ahead and I'll put VB is equal to negative V over R2 over R1. The first point that I would like to make is that we said VA was grounded. Put grounded here. Grounded. Notice, however, that even though VA was grounded, current was still able to pass through that node. It wasn't a true ground, if you will. If it were a true ground, in other words, this, if we had this labeled on a diagram, okay, I'll call that true ground. In other words, true ground serves as a sinkhole for current. If you have something attached to true ground and you're at, a high potential, then current will flow and kind of exit the circuit, right? Think of it, just think of a building with a lightning rod. Okay? Lightning strikes the top of the building, it flows along the circuit, and it goes into ground, and it, if you will, disappears. It exits the circuit. Okay? That's what I think of as being true ground. It provides not only a reference point from which potentials are measured, But in addition to that, it serves as a reservoir for charges. So I'll call it a charge reservoir. Okay. Here, if we go back and return to our operational amplifier, here we have something slightly different. Okay. The potential is 0, okay, but it's not like the charge is being removed from the circuit or charge is being added to the circuit, like what true ground would actually do. This is sort of like ground, but not. And so we call this a virtual ground. Virtual ground. That's just to specify that the potential is 0, but any current that's going through that location isn't lost. And what I mean by lost, it's not dumped into the reservoir and exits the circuit. Okay? It's that charge moving through still stays in the circuit. Okay, so that's one idea. Okay, we have a virtual ground. The second idea is going back to the amplification of the output signal, or the amplification of the input signal, excuse me. You notice for a moment that VB, you could think for a moment that I could, with the appropriate choice of resistors, I could end up with an output potential dramatically larger than my input potential. And what should bug you about that? You got some ideas? What should bug you about this? Quick, what are the units of potential? Volts, good. Volts. And volts are equal to a joule per coulomb. So I return to this idea about what happens. Conceivably, you could end up with an output potential much, much larger than the input potential. A different way to say it is you could end up with more energy per unit charge than what you started out with. How do we correct this idea? It's like if I hook an op amp into a circuit, I get free energy. No, you know that's not right. Something's goofy here. Where did the charge come from? Right? We have some output charge. Where does that output charge come from? From the operational amplifier. From the power supply, right? The operational amplifier has some power supply inputs, and those power supply inputs can provide current. And if you ignore those power supply inputs, if you don't draw them, you might be inclined to believe that charge conservation is violated. Similarly, we are now seeing how we can account for the apparent violation of energy conservation. Those power inputs, not only do they provide charge to the circuit, okay, if needed, but they can also provide additional energy. In other words, you can end up with an output potential that's much higher than the input potential. It seems like there's extra energy being created. Oh, nay, the excess energy is being delivered by the power supplies to the operational amplifier. Okay. Other point, if you power an operational amplifier, let's say that the power for the operational amplifier is 10 volts. So you run plus 10 volts on one side and negative 10 volts on the other. Put volts and volts. Okay. What do you think? What does your intuition tell you? What do you think the maximum possible output would be? Got it? Good. Remember, energy conservation will still hold. Maximum possible output. So VB will have to be less than or equal to 10 volts. Okay. So bear that in mind as well. When you're designing a circuit, when you're playing around with the circuits, bear in mind that the operational amplifier can increase the output potential based on your choice of R1 and R2. But there's a physical limit. There's a limit to how much potential it can produce. Namely, the output potential can never exceed the power supply potentials. Okay? Incidentally, say for example, you choose a value of resistors such that the output potential is greater than the powering potentials. We use the term saturate. Well, I think that's it for the moment. We'll keep this video a little bit shorter, but go ahead, start reading through the chapter, and they'll provide this this simple circuit, this inverting amplifier. They will also show that one in your textbook. It's a standard one that just to get your feet wet and kind of understand what's going on here. Okay. We'll do some more examples both in lecture and in lab. And yeah, we'll keep going. Hey, thanks for your attention. I'll see you next time.